Okay, so it's something that I've been wrestling with for the last several years is trying to figure out where the dividing line between memory and storage is. Just a bit about my background is I come from an IO environment in this large scale up simulation world where we worry about very large data sets and how to be able to manage the data so that scientists can do their analysis on them later, but also write them out to some sort of stable storage so that they can continue to do as much compute as possible as fast as possible. Because it's difficult to get enough science done. So we basically try to figure out how do we get as close to peak bandwidth out of our storage system as possible. And with these new kinds of devices coming online, we're trying to figure out how do we end up using these for best advantage in this environment. And part of that, is not having storage in the way anymore, but trying to do things more direct memory to memory. But there's challenges there, and I'll go through some of that. So this is the kind of the scale up size of the kind of applications that we deal with. So single task, very large machine, enormous size for variables. So we might have anywhere from, say, 5 or 10 variables up to 50 variables for a simulation, but the aggregate size of those will be a half a petabyte or even a petabyte. And that has to be spread across all of our different nodes so we can get our compute done on it. And all is done synchronously. So if we're going to do a simulation of the atmosphere in this room to try to look at where and how all the cooling vents work, we'll have to have a mesh that describes the volume of the room, including all of the intermediate data points for all of the area in here. And then we're going to have some physics that we're going to apply to all the different points, and that's going to cause all of our different fluid dynamics to occur and that sort of thing. So that's the kind of thing that we're looking at. But we're more dealing with very large scale simulations, such as maybe weather or climate kinds of things that may go up to the entire globe or other things like that. So in terms of our machines, big machines like this is similar to what we're looking at buying for our next machine. I don't know how much this is actually public information, but I think it's generic enough that I can get away with describing this. But we're looking at somewhere in the realm of about a petabyte and a half of RAM, 200,000 cores, about 100 petabytes of storage, and dual 200 gigabit network links on every node. The thing is that's pretty much just a system on a chip on a card, and then we just have a lot of those hooked together with this really fast network through switches. And we had multiple bids that looked very similar to this, which is why I think I'm okay describing this way. So, but that's the kind of machine that we're end up dealing with, and we want to use most or all of that for a single application task in order to go through and do our calculations. So the questions that we end up asking is how do we end up doing something that is more effective in order to get more science out of these machines, because we're buying these machines to get science done. And we don't look at things and saying, well, we're not going to use as much energy because the energy is too expensive. We look at the total cost of the machine and it will say, okay, if we slow down the calculation by 1% and we can save 5% on the energy, if you just look at the cost of that energy versus the lost compute in terms of the overall cost, it's actually a loss. So we actually try to figure everything in, and we really try to maximize the amount of compute that we can get out of the machines. So where can we bring in persistent memory? There are other places like trying to do workflow kinds of things, which is also something that I do. And is persistent memory versus NVMe or other kinds of devices, is that the right solution for us? Because we also have a budget we have to deal with. It's not like we have a completely blank checkbook. So that last machine is somewhere, from what I can understand, in the 100, 150 million kind of range. It's not an enormous budget for that kind of a machine, but it's also significant. So the things from a storage standpoint that I've been looking at, since that's closer to where I end up living, is that we went from basically having disk and tape to getting something where we started introducing flash, and we're trying to look at, okay, how can we make flash work? And then, as Maya brought up, Gary Grider said, let's do these burst buffers. And it turns out that grew out of this data staging idea that we were doing at Sandia many years before that. And the idea with data staging is we set aside some of the compute nodes and said, let's just use them to take all of the data that we were doing this massive calculation on and then pull everything there, because we had this very communication intensive task, and run that there instead, and then we can pull it back out. And it ended up getting like a 10% performance improvement, even counting the additional node hours that were consumed for that. So that idea ended up being morphing and saying, hey, let's try to do this burst buffer thing. But the other thing that was happening, and the graphs that Gary always showed when he talked about burst buffers always showed two graphs. One was the price for capacity of disk, and the other was price for capacity of flash. And the thing that he never really did was looked at where they crossed over. He just showed that based on performance, we could afford so much flash to be able to get us the kind of performance that we need for the short term, but we need the disk for capacity. Because previously, when we were buying disk, we were looking at it and saying, I need this much bandwidth to be able to get my data out of my compute area fast enough. And then you look at the aggregate storage, and it's like, well, I have more storage than I can actually use, so I'm getting storage capacity for free. So with quad level cell flash in particular, the price for capacity is just about the same. And because of that, we're in a realm where we have more bandwidth that we can use, and we're actually having to buy for capacity again. So in terms of memory, you all are better experts on this than I am. But the shift that we're dealing with Sandia right now, and also I'm sure on all the other big machines for the labs and other places as they get bought, is that we, for our kinds of simulations, are very much memory bandwidth bound. And because of that, we try to figure out how fast can we basically churn through memory. And with the offering of high bandwidth memory, we look at it and say, okay, if we can get memory that's closer to the internal clock speed of the CPU rather than the external clock speed, we can get significant performance gains without having to have a lot more compute. That also means we use our cycles that we have available a lot more efficiently. So that's what we're looking at for this next machine, is that we'll have, say, 48 cores per node, but 64 gigs of on-package memory, and then we'll have no DRAM externally. In fact, in some cases, we might not even have slots. And if we don't have slots, then we don't have any extra places to put things. But if we do happen to put slots there, then we'll have options of either having additional DRAM or potentially persistent memory, which would be an interesting choice. The other pieces are, and we've also talked about that yesterday and today, is having sort of in-network provisional or provisionable memory. And that's something else that would be a potential option. But that's another thing that we're still not 100% sure how to use effectively, because these big machines are not single user. They're very much multi-user, and the applications that are running on them change pretty much continuously. So you might have a very large application running that takes up most of the machine, but then the next day or a few weeks later, you may end up having 30 or 40 applications running. And as these applications churn through, the ability to say, well, I'm just going to leave my stuff on the node, that's not really an option, because every time somebody's job comes in, they assume they own 100% of the node and all of its resources. And because of that, we have to be able to deal with, okay, if we're going to save that data, we have to stage it out somewhere. If somebody expects it to be there, we have to stage it in. And those kinds of things need to be added to our system management kinds of things. So we look at all these things and we say, okay, persistent memory is really promising in terms of its performance and capacity advantages and price for capacity. How do we fit it into this picture and try to make it usable? So these are this is where I ended up kind of getting stuck. Is I looked at it and I said, if we look at it from a memory perspective, persistent memory would end up kind of being the slow tier. But I looked at it from a storage perspective, persistent memory is the fast tier. And I started talking to some of our people internally and asking them, so what's memory and what's storage? Not really directly in this context, but just in general, how would you describe something that was memory versus something that was storage and how it's used? And I got a lot of different answers. And to be honest, it was never really very consistent. And I thought I had an answer. And then unfortunately, that answer got destroyed recently. And I'll describe that here in a little bit. So in terms of storage, the 4 assumptions that seemed to be fairly consistent was your data lifetime was longer than your application runtime. And for some people, they may look at that and say, well, maybe it's just transient data storage and I have it staged there until the application picks up again. But that's really, I'm using that like memory. It's like, okay, but still that's more of a storage use case. The thing that I got through based all my thesis work and such was looking at I/O and data formats. And that was when you store data in, with the intention of putting it in an archive potentially long term, you encode in that data the information to be able to then read that data back and understand it. So you know things like endianness, you know the things like the size of the data types, and you know the layout of the file and those sorts of things, so that you can then go back and re-extract the data. But that's not necessarily true in memory. The architectural assumptions, so like big endian versus little endian, that's another one. And then um, we assume that storage is slow, so we try to avoid it. Was there a question? No, okay. So flipping it around the other way, if we look at something and say, okay, well, I'm going to treat this like memory, then it's okay. The data only lives as long as the application. We don't bother putting any metadata into our actual data storage because we want to be able to have as much data density as possible so we can compute on it as fast as possible, which makes sense. You don't want to pollute your caches with metadata that you're just going to skip. And then reading and writing are essentially identical kinds of operations. We don't worry about them that much. And reading and writing is fast compared to storage. So now if we add persistent memory to it, if we look at it, which ones of these does it really fall under? And didn't really come up with a great answer to that, unfortunately. The second one, which I think is more of a question we've kind of wrestled with a little bit this week or the last couple of days, and we've kind of come to a conclusion that persistence, does it matter? I think the answer is no. If anything, it might be a penalty. And then what happens if it's not local? And that's something else we've touched on a little bit, and that's something else where we're kind of treating it like a storage device because it's not locally, but we might be doing RDMA access to it. So is it memory then, or do we care? And that's kind of the question: is do we really care? And the last one we've had a lot of discussion on is it really block oriented or is it byte addressable because you do load and store instructions? And the fact is that there's always some level of blocking to it. It's just a matter of how big those blocks are. And I don't know that really matters that much. So these are kind of the questions I ended up running into. So if we're organizing data for the highest density, that's pretty much from what we were able to figure out. That's really more of a memory focus on things. But if we organize data for a long-term storage and archiving, that's really more of a storage kind of activity. So those are really kind of at opposite ends. So if we're writing an application checkpoint to disk, depending on how we do it, it might be memory or it might be storage. For some applications, they just say, I'm going to copy exactly what I have in RAM and write it to disk, then I can read it back in later and restart. Other ones say, no, let me put it out in a structured format so I can then use it for something else. And that's the first one is treating it like memory, but the second one's treating it like storage. And then the ones that really kind of got me were the European Center for Medium Range Weather Forecasting. They recently had a re-architecture of their system. So what they do is, like every 4 hours, they have to deliver a medium range weather forecast, which is like 10 or 14 days out or something. And so they had this continuous process that's running that's generating the forecast, but they also have another much larger set of compute that goes through and looks at all of their old forecasts and compare it against the observations to try to help them improve their models. And what they realized is that they were doing a lot of work converting data from one format to the other to be able to work on it. So they just decided we're going to keep everything always in the storage format and just compute on that directly, that the difference in performance was not big enough in terms of the compute loss for them to care. So at that point, they've completely violated what I was looking at was the difference was, is your metadata there or not? And they've just decided this is going to be something better. So in that case, then I've kind of hit a point where is it specifically one or the other, or is it really both? And it depends on how you use it. And I think it has to be both. So the applications people are the ones that we really care about the most because we buy these machines in order to run these large-scale applications on. And if we tell them that we have this very large capacity additional thing that's accessed through the memory bus that has load and store instructions, they say, great, I got extra capacity. Sure, it might be slower, but I can actually do a bigger compute on the same node. I don't have to work as hard to try to parallelize everything. And they're very happy. The thing that might be a little more challenging is they might have to end up dealing with an out-of-core kind of compute model where they say, okay, I'm going to do everything core in my high bandwidth memory, then I'll swap out to the persistent memory just as a way to be able to keep as much in-package computing as possible. But then you got to deal with all of your swapping out and other things like that. But that's the kind of thing that they've done in the past in some cases. For the storage people, they look at it and say, great, my job is to make sure that I provide a consistent, persistent checkpoint as fast as possible and absorb persistently all of the data the applications people want to push as fast as possible. So they say, great, it is really fast storage that's close to the compute. and that's the way they want to use it. And the problem is that both of these people are correct, and it's just a matter of you end up having to balance between the two. How do we make this work? And Joe was actually great yesterday afternoon because when he came to his conclusion and said, here are the 4 things you need to keep in mind when you're dealing with persistent memory, it's exactly the same 4 items that we as storage-related people say, these are what you have to keep in mind when dealing with storage. So at that point, it's like, okay, when you're evaluating persistent memory, if you come to the same conclusions as you do with storage and the same conclusions that you reach with memory, I don't think that there's a way that we can physically classify this as one or the other. So in terms of the winner, if we were going to say, does it have to be memory or does it have to be storage? In general, we always default to the apps people winning, which has always been a frustration for me because, like, for example, we worked very hard to shift all of our I/O to be asynchronous to avoid all of the massive communication phases. Then the applications people looked and said, you know, we're not actually doing any communication while we're doing all this compute. Let's start doing a lot of asynchronous communication there. I told them, wait, no, stop. That's when I'm trying to get out of your way and do things. I was like, they said, well, how much data are you moving? I said, a lot. And they said, no, it can't be that bad, because they were looking at maybe a couple of megabytes here and there. I said, I need to move gigabytes during that time. And then they're like, oh. I said, yeah, and if you start doing asynchronous communication there, then my asynchronous communication happening at the same time means that both are essentially going to be synchronous. And at that point, then we're now having a tug of war trying to figure out which one is going to save the most amount of time over time. And the applications people, since they end up running 80 or 90% of the time, they tend to win. And they just say, get faster storage. Or they'll say, I'll write a little bit less data. But they end up basically getting what they want most of the time. In terms of the programming side, though, that's actually the bigger case, and I think that's where all of you will come in and really contribute the most to this discussion, is what's the right way to program to these devices, and how do we make them the most useful? In terms of transient data staging, that's actually the one that's more important for me, because I do a lot of workflow-related work as well. And what I look at it is, if I need to take 2 different physics simulations, or a physics simulation and an analysis routine, and I need to connect the 2 of them, and I don't want to have to write things to storage, I need a large capacity place that I can stuff some data, and I need to make sure that that data set is complete and correct before somebody tries to consume it. And if I can be sure that that data is stored persistently, a lot of my problems in terms of resilience go away, because I no longer have to say, well, if one of those nodes goes down because we had a power outage or whatever else, then I'm going to have to go figure out how far back I have to go into my workflow to restart things. It actually makes my job a bit easier. And plus, having that additional capacity gives me more places to stuff things. So in terms of the bottom line, what we end up looking at is the data lifetimes. There's not really a particularly interesting difference, because we'll end up either storing it for the long term or we won't. And if it's cheaper capacity, if it's persistent, we don't really care, other than the fact that, well, I now have to erase it. So that may be the penalty that we look at in terms of the persistence. It's almost a penalty rather than a benefit. The speed difference is also something I don't think really matters as far as this discussion goes. I think that the difference between, say, registers and persistent memory versus persistent memory and disk, those ratios, while granted they're not identical, they're close enough in terms of orders of magnitude that if you're trying to make an argument, there's not a strong argument saying one is significantly closer to the other than the other direction. And because of that, being able to use devices one way or the other dynamically based on which application has to be loading at the time, that's a better way to think about things. And that data encoding, I thought, was okay, this is the one difference, but the weather people ended up messing that one up for me. So in terms of what we really need to do in terms of making these big applications work, is that memory copy is the kind of thing that the application people would really like to do. They just like to say, oh, if all I have to do is memory copy my variables to a new address space and I'll be done, that would be awesome. Then I don't have to worry about these I/O APIs. I don't have to worry about my file formats. It all just kind of magically work. That'll be wonderful. Problem is that there's a whole lot of things that don't get taken care of that way. One of them is, actually, I think I have it on the next slide, so I'll come back to that. But the um, the moving data from one location to another, the difference there is something that we've had to deal with at Sandia because we're trying to make it so that we can have performance portable code between different kinds of devices. So if you have a CPU or GPU accelerator or even an FPGA or something else, and you want to be able to have code that can run on any of them, you need to have a way that you're managing how you're taking the data that's going to be computed on and put it into the right address space for each of those. And Cocos is the library that's part of that, and that's being worked into the C++ standard as quick as they can manage. And the byte to block piece, I don't think that really matters because we can put a byte level interface on just about anything. Performance, yes, that becomes an issue, but we can put a byte level interface in front of anything. The last one, which is probably the most important for us, is when is everybody else going to really support persistent memory? And if they don't, then we're kind of stuck with a one vendor solution. And whether or not that's something we can really rely on and use is kind of a different question. We did with the Roadrunner machine go down the road of having a completely different kind of architecture and adapted to it. But whether or not we'd make that investment again on something that didn't have broader support is an open question. So the first one here is what I was alluding to on the previous slide was, since we're trying to put things into an archive format and you're just doing a mem copy, how do you then annotate all of that data in a way that could then end up being read later automatically? And that's something that can be put in a new memcopy command, where you just have a fancy thing where, depending on the kind of thing that gets passed to it, it's smart enough to know what it needs to do, and it can build these buffers for you automatically. But that's something that would need to be figured out. The whole architectural changes on the machine, that's definitely going to happen because it has always happened and it will continue to happen. I don't see anything potentially being static. And the last one here is archiving. And this is something that the DreamWorks guy was also talking about, is what do we do with this stuff long term, and how do we deal with the fact that things version over time? And we need to, just from Sandia's mission perspective, we have simulation data that goes back decades that we need to be able to go back and look at again. And if we don't write it out in a format that is accessible, then we have no ability to then trust what was there or anything else like that. Virtual machines, I think, are a mostly, but maybe not complete solution to this, but that's a whole different discussion in terms of how our machines are organized and that kind of thing. So that's what I have.
I thought it was interesting that PCI on version 4 finally realized they needed version.
Yeah.
I would have thought that would have been version 1. They could realize you need a version number, so you can say, oh, this is this type of packet, this is this type of packet, rather than just assuming everything's the same.
Right. Yeah. Well, wasn't that introduced about the same time that they had slot 1 as their CPU interface? It seems like it was about that same time. And so it was just an assumption that, oh, this will be the interface that you just put new stuff in. And granted, waiting until version 4 is a long time to admit, well, maybe we should do something different. So, yeah. Any other questions or comments? Yes. Yeah.
Storage of memory in the kernel. If I have to talk to the device driver, I think it's in the storage mode. And if I can steer with like in kernel memory management APIs in the memory, and we have this debate.
Yeah.
Should we do a memory interface for the storage?
Right. Yeah. Right. That's a good distinction, because that's something that I hadn't really thought about. So as you can see from this, is that I really think about computing in the very large. A lot of the things we talked about yesterday and today has been very much about the single node thing. And I'm relying on all of you to make sure that works, because I don't have time to worry about it. I just need to assume that it works, because otherwise I can't do anything with it. So please keep up the good work. Anything else? All righty.